Hello, my name is Shin. Here is a description of a method for dealing with variance that was published by Jujutsu Hiransia in Japan. In this video, I explain the motivation for publishing the method for dealing with variance, the difference from existing probability statistics, its strengths and weaknesses. I will explain the cases in which you should use this method of dealing with variance and the cases in which you should use existing methods. In existing probability statistics, it is common to extract information such as mean and variance from a sampling of a population and then test its validity. In contrast, when a population contains multiple mutually independent sources of variance and the relationship between them is known, a histogram is extracted for each source, and a population distribution is generated by combining them. This is because the object of design and analysis is often a population of such complex objects. If such a population is sampled according to conventional probability statistics, even a large number of samples may not be stable, but the information extracted for each source of variance provides exact information on the population from which it is assembled, even with a small number of samples. This section will explain the motivation for proposing the above method of dealing with variance. The motivation for proposing a method of dealing with variance is the 3 steps described here. First, when the results of calculations are used to make judgments, such as the calculated value being above or below the criterion, or the result of a simulation showing a collision or avoidance, the variance and the parameters used is generally handled in the conventional probability statistics in the form of mean or variance. I believe that the calculation is made with an average value, etc., and a judgment is made as to whether the margin between the result of the calculation and the reference value or obstacle is greater or less than a multiple of the variance. In this case, when using the standard deviation as the variance, it is assumed that the variance is normally distributed, and the portion of the actual distribution that has a different shape from the normal distribution is an error. However, by treating the calculation of this parameter as a distribution based on actual data, such as a histogram, rather than processing it as a mean or variance, various excellent judgment indicators can be used, such as the percentage probability of exceeding a standard, or the percentage probability of approaching a certain distance. This means that information that has been filtered out before calculation in the conventional method is inherited and utilized in the calculation results, thereby improving the calculation accuracy. As mentioned above, there are many excellent decision-making indicators that can be obtained by accurately determining the shape of the distribution of the parameters that form the basis for decision-making. In another video on this channel, I discuss the use of distributional indicators to compare the positional relationship between 2 distributions, to determine the exact probability of proximity, and to determine the exact point at which the accumulations balance out. By using these techniques, I can see how our judgments based on numerical values alone have been ambiguous and contain large errors. I believe that these technologies will improve the various judgments made in industrial and economic activities and reduce the number of glitches and errors. Many existing probability statistics compute the mean or variance of the parameters needed to make a decision for a population, but some also compute distributions. Still, when one tries to obtain a general shape of the distribution as the result of an operation, it is possible to make a reasonable approximation, but the degree to which the shape of the distribution is guaranteed is ambiguous. For example, Monte Carlo and Bayesian estimation methods can asymptotically determine the distribution by performing iterative operations. However, there is no guarantee how much error will remain in the distribution shape after how many iterations. In fact, when I try to obtain the distribution using random numbers, the mean and variance can be obtained accurately, but the distribution shape may not converge to a certain distribution even after a huge number of iterations. I believe that distributions obtained using the Monte Carlo method or Bayesian estimation will not give satisfactory accuracy results even if we use the decision indicators mentioned earlier. There are also methods such as stochastic processes, but they can only be used in cases such as random walks, which are assumed to be a specific path and converge to a normal distribution. When using standard deviation, the assumption is that the distribution is normal. If it is approximated by a normal distribution, errors due to differences in the actual distribution can be magnified as much as possible if there are multiple factors of variation or if the amount of variation is large. Errors due to the method for dealing with variances handled will become smaller if the distribution is broken down into smaller pieces. When generating a distribution from data, conversion errors due to kernel distributions, etc. will occur. Therefore, I believe that quality can be improved by managing parameters as much as possible as a distribution and aiming for a highly accurate distribution. Furthermore, a population, as discussed in probability statistics, is assumed to have a single source of variance, and I believe that random sampling will converge to an accurate distribution with a relatively small number of sources. However, the population of an entire object, such as a design object, an analysis object, a complex physical phenomenon, or an economic activity, is often a combination of variances of various mutually independent factors. When data are randomly extracted from such a population, distributions such as histograms may not converge even if the number of sampling is very large. This is because such sampling is only a specific combination of independent factors of variance, and if there are many factors, the combination becomes enormous and cannot be regarded as equal data. However, if each of these factors can be sampled separately, the distribution of the population can be stabilized with a relatively small number of samplings if the distribution of the population is obtained from the histograms of each of the individual samplings, taking into account the combinations of each of the relationships. To make this possible, I thought it necessary to find a way to uniquely determine the exact distribution of the population from the distribution of each factor. The distribution operation, which extends the numerical values of the model to distributions, is used to obtain the distribution of the population by considering combinations of the distributions of each variance factor in relation to each other. Therefore, if the population can be decomposed into several variation factors and the relationship between each factor is clear, then the method of dealing with variance described here should be used. If the factors cannot be decomposed, the existing methods will not cause much error. Decomposing the factors without any leaks and accurately identifying the variance in each of them is the way to ensure quality. Later, I will discuss in more detail the cases in which a single factor of variance in the population is involved and the cases in which multiple factors are involved. This figure illustrates the difference in sampling, as explained in the third paragraph. Existing statistics, whether it is frequentist statistics or Bayesian estimation, often obtains the population rather than decomposing the variance into factors. The mean and variance are obtained from a randomly selected sample from the population and examined to see if they are reasonable values. However, if the population contains multiple mutually independent sources of variance, even if the sampling data is very large, the number of combinations of parameters for each source will be enormous, and the shape of the distribution is often not guaranteed from the randomly extracted data. In other words, even if the law of large numbers is valid for a single variation, there is still a degree of freedom in the combination of multiple factors, and the law of large numbers is not valid for the total of multiple combinations of factors. In contrast, in the method for dealing with variance, a distribution can be obtained for each factor of variation, and the distribution of the calculation results can be obtained by using the distribution as the calculation target. If the data is for each factor, a stable distribution can be obtained even with a small number of samplings, and the parameters of each distribution can be divided and combined to a small degree to obtain the exact distribution of the resultant population. There are several existing methods for estimating the overall distribution from components, which I believe apply standard deviation, Monte Carlo methods, stochastic processes, etc. I have explained in the video presentation of the published paper that these may not approximate or converge to a stable distribution, such as a normal distribution or other functional distribution. The following is a specific example of a case in which the population can be broken down into multiple sources of variation and the relationship between each source is clear. The first example is when designing hardware, software, or a system that combines them. In this case, the factors include all the variance factors that affect the performance and reliance of the hardware and software components and functional parts, such as their dimensions and the environment in which they will be used. The population includes the quality, such as performance and reliability, of the finished product in the market. For example, in dimensional design, where performance and reliability are determined by a single dimension of a single part, a small sample of data on the dimensions of the finished product, the population, can provide assurance. However, if the dimensions are a combination of multiple parts made at multiple factories, each dimension varies independently, and the finished product cannot be guaranteed with a small sample. If it is a finished product, it will not be stable unless it is a very large sample, but if the distribution is created from the data of each part, and the distribution is synthesized by distribution calculation, then each component will be stable even with a small sample. This is because the distribution calculation takes into account all combinations of the variation parameters between parts and generates a distribution of the finished product after the calculation. In cases such as variance, where an oversight directly leads to a defect, an accurate method of correlating individual variances to the overall variance is a powerful defect prevention measure. The second example is the case of predicting the motion of an object, the environment, or a physical phenomenon using simulation or other methods. To account for variance in such cases, Monte Carlo simulations are often used. A Monte Carlo simulation is an iterative simulation with random numbers generated according to a distribution of individual parameters to obtain a distribution of results. Although the Monte Carlo method can obtain the mean and variance of the results with high accuracy, it may require an unrealistic number of iterations to guarantee the shape of the distribution of the results, since a huge number of combinations are assumed due to the fact that many parameters vary in a time series, and the distribution of the results obtained is practically not guaranteed. In particular, I believe that simulations with large variances in the time series or with divergent trends in the results will have large errors. By understanding the distribution shape of each and every influence factor and analyzing this by distribution arithmetic or distribution integration, the distribution shape of the results can be stabilized. For the third example, I believe it is possible to analyze various economic and market trends by capturing the balance structure of market principles as a balance of distribution, as proposed in the video of the decision index by distribution. Economic activities require consideration of various variation factors such as business and consumer trends, income, and production efficiency, and I believe that such phenomena are compatible with distributional operations. Since there are still few examples of analysis in this field, I would like to increase the number of examples of operations while studying various textbooks. I am looking forward to learning more examples from various textbooks. Another example that cannot be broken down into individual factors, which does not need to be dealt with in the method of dealing with variance, is when there is no more than one factor to be considered, such as in TV program ratings surveys or product sales forecasts. However, as clustering technology using AI has advanced in recent years, there is a possibility that these preferences can be broken down into their constituent elements and their relationships clarified, and by processing such factors and relationships in the method for dealing with variance, it may be possible to dig deeper into the data than ever before. The following is a summary of cases in which you should use the method for dealing with variance. First of all, existing probability statistics provide relatively accurate results when determining the mean or variance of a single source of variation in a target population, but they do not provide accurate results when determining the desired probability distribution or exact probability value when there are multiple mutually independent and complex sources of variance. It is in these cases that the method for dealing with variance should be used. Therefore, the method for dealing with variance provides a highly accurate computing environment for design, analysis, and various simulations. That concludes the video. Here is a link to the site where the tools for using the method for dealing with variance are located and the site where the book is available for sale. Thank you very much.